Okay, so we are throwing people out of elevators. Weird. Helicopters. Sorry. Uh, can I make one helicopter comment before we get comfortable? So let's do this problem. Now, it turns out that there is a whole lot of writing that we could do. We know that gravity pulls down, and we don't have to write all this unless you're just dying to. Now, for the sake of this problem, we're going to assume that gravity pulls down. We're just going to call that positive, which means air pushing this way, according to Newton's third law, is going to be our negative value. Are we okay with that? So if we're looking at this, we can think about it with velocity, but we're changing velocity, which means we're accelerating. We're going to use the following relationship. We did not discover this, but I'm just going to tell you that this is true. If you are dealing with the basics of air resistance, the rate of change of your velocity, it turns out, is not terrible to write. We can simply say that this is gravity. And remember, gravity, we're thinking positive downward. It's just gravity, and it fights against some constant k times the velocity. Now, just like your moment of inertia or how hard it is to make you spin, that's what the moment is. It depends on where your mass is at and stuff. That changes. We are assuming in this problem still something nice. It's a uniform object. So if it's a person that does not change the shape of their body nor the way that they're going through the air. There's the same area hitting the air as they fall. Like we could have done a sphere, but then it doesn't work quite as nice. This value of k depends entirely on the object and the way it's oriented. So we're just assuming it's nice. Everybody cool with that? Now, this thing right here, if we wanted to solve this differential equation, could we? Could we separate it, do you think? I think so. We could just divide each side by g minus kv. We could multiply both sides by dt, and we could do the whole process. It gets kind of gross kind of fast. Now, if we don't want to have to do that, because even if we found the equation, do you agree that their speed probably depends on like how quickly they jumped out? So I don't want to have to plug in a bunch of different numbers. It would be really nice if I could look at a whole bunch of different solutions to this without ever having to solve it, and I could just look at all the graphs and pick different initial conditions. Hold on. A way to view all of the solutions at one time. What did we talk about yesterday? Slope fields. And what are slope fields? How do we define them? A way to graph all of the general solutions, like all the possible answers of a differential equation. We have two options. For this one, we could either integrate it and solve it and try to deal with it and then plug in a bunch of different v values, or we could just create a what? Slope field. So we're going to work in America units today because that's what I did this problem in. I don't know why the book doesn't even have this problem. I had to find this elsewhere. But we're going to go ahead and go with a couple things. So for our problem, we're going to say it's some person, and I'm just going to give you some values. Let's say that g, for our purposes, we're going to call it 32. And it's 32 feet per second, which turns out, feet per second squared, I'm sorry, which it turns out is the same as 9.8 meters per second squared. Okay? And then for this particular person, let's say that k just happened to be, calculated by physicists, thankfully, 1.6. That's our constant. Now, what I want you guys to do is you're going to make me a small slope field. And I'm okay if you guys do this up on the board, but we're going to notice a couple really awesome things about this. This never changes. What's the only variable in here? V, which means no matter what t is, doesn't matter, the v values are always the same. So I'm going to have you make a small table, and I'm going to start the table here. We're going to have v and dv dt, which this is like velocity, and this is the slope of velocity. Okay. As you're going through this, whether you physically construct this table, like you're obviously drawing it now, but if you just calculate them in your head and then draw it, I'm okay with it. I want you to construct this table by increments of 5, and I'm going to have some dot, dot, dot. We'll go 0, 5, and I'm just going to do it this way, dot, 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 and I want us to go all the way to 40. So the 0 is a situation when we just walk off the edge and there's no initial velocity downward. This is when we jump down at 40 feet per second. Like that's our initial velocity. I want you guys to construct the slope field for these values of v. Cool. I'm going to give you a moment. I'm going to pick your groups real quick because I think you've picked them the last few days. Differential equation is that every single thing jumps by 5, right? So that's really convenient. We decided t and v, and then we're just going to go through here. When the velocity is 0, which happens here, and each of these this is 10, just so you know. So each of these places is where the velocity is 0, based on my graph. Do you all agree with that? Because v is the y, and here's where all of them are 0. So 10, 20, 30, and 40. The cool thing about this is all I need is v. I don't have to worry about the time. Turns out, doesn't matter. What is the slope when the velocity is 0? Or if I reword it, what's the acceleration when velocity is 0? 32. Okay, which means this is not going to be to scale, for sure. 32 is almost what sort of line? Something with a slope of 42. Like, it should, imagine a line y equals 32x and show me what it looks like with your arm. Almost straight up, right? Almost. Which means all these should be super steep. They're not quite vertical, but do you agree that that is pretty steep? And is this the same v value and there's nowhere to plug in t? All these should be the same steepness, right? All of these will be the same steepness. And I'm just trying to make them kind of nice. All of these are the same steepness. Is the same thing going to be true at 5? Will they all be the same steepness? Like, not the same as this, but just the same as every other 5. What's the slope at 5? 24? Is that more steep or less steep than this? So let's see here. Do I have enough room? We'll say here's 10. I'll go back to yellow. And I'm going to do one more point with you, and then here's my 5s. So a little bit less steep there. Okay. So a little bit less steep. It's still pretty steep, but is that a bit less steep? And is that a bit less steep? And less steep? And less steep? And I'm just doing the same thing. I'm going to copy and paste all these on mine. This is all that we're doing. I want you guys to get your slope field, and then we'll see why I'm making you do this. Whoa, why did it go up to 40? That was super weird. That's okay. At 20, was it 0? Yeah. You speak German? Riley, do you see why that's the case? Or Kalisha? I don't know who you're talking to. Okay. Oh, it's interesting how they're all kind of going in the same orientation toward. What's 10, Sean? Is it 16? So it's just a little bit less steep. Okay. Is my screen still on? Okay. Without you just copying, are you doing the same thing that I am with your group? Are you getting the same stuff? Okay. Oh, I'm still recording, so that's a waste of time. Oops. I want to think out. What's one possibility that I could jump out of the helicopter with? If I just walk out, what's my initial velocity? So here's the big part of this. And if you guys want to think about it for a second, I can leave it if you want to play around with it, but we can see the solution. In fact, we see all the solutions without solving it, at least roughly. If I start with this initial velocity right here, is it clear that there's a curve that this is going to follow? And here's the cool part. If I work this way, it's going up a lot at first, right? Then what's it do? It gets a little less steep, and it keeps getting less steep and less steep until it gets to here. What does it eventually settle on for the velocity? Is it 0? So remember, this, it is 20. This is the velocity in time. We settle at this, 20 feet per second. What if I started at 25 initial velocity? It starts here, so I start slowing. Why would I slow down if I jump out? Because air pushes me. The faster I go, the harder air pushes me, in fact, because I'm moving through more air. Does this one, even if I start fast, I start to slow down a little bit, what velocity do I kind of level out at? What if I started, I don't have it, but what if I started up here with an initial velocity of 60? What's it going to do right when it leaves? So explain to me how it's going to curve. So yeah, it's going to decay exponentially, something like this. Can we see that it's following those paths? We have just discovered there's a word for this, and Sean recognized it right off the bat. If I drop something, the fastest it ever goes, there's a name for that. It's not optimal speed, but you're close. This is the terminal velocity happening, and terminal velocity only happens because of air resistance. Okay, if this problem seems awful, that's fair, but here's my option that I have for you. We're done with this section, pending one last example if you guys would rather do this than slope field stuff. We can do more slope fields if you want practice. But here's the other thought. Do you want to go through the process of actually solving this differential equation? Like, it won't hurt. It's not terrible. Should we do a little bit of algebra, calc practice stuff? Okay. Was this terribly hard to do? It takes quite a bit of time, for sure, but it's not wildly hard. This differential equation is not wildly hard. It's a little harder than the ones we were doing yesterday, but this is nice to just get an answer if I just need an answer, right? Like, I can even tell, based, if we do our scales and stuff, I can tell you how long it's going to take for me to reach my terminal velocity from this graph. We get so much information out of this. Okay, now, if we wanted to actually calculate it instead of approximate it by looking at a graph here, we need to solve this. So what we just had here was the, I don't want to say easy, but we'll just say less taxing approach, which we get an approximation, but we don't get an exact answer with it. Like, we'll get really close though. In place of that, let's actually knock this out, and we're going to do some heavy lifting. I want us to actually solve. Nope. S certainly, but not that one. Solve this equation. dv dt equals g minus kv. And we got to be really careful. Where I should probably make some comments about a couple different letters that are written here. What's the variable? V. What are g and k? G and K are constants. Nice job, Abigail. Are constants. All right. This one's going to take a couple minutes. If you need a brain break in the problem, I won't know that unless you do what? Bet, bros. All right, let's do it. I'm stuck. I need all the V's and stuff on one side. Thoughts? One more time. Ooh, this could be a board problem too, but I'm afraid it might be a little too hard. Divide by what? We already closed on that, Clecia. Thank you. So I like the idea. I should divide by something. I just need to know the something. Thoughts? If it doesn't work, we'll try something else. G minus KV. All right, let's try it. I'm going to divide by G minus KV and multiply by dt. Okay, so I'm going to rearrange it. We would get G minus KV, sorry, dV over that equals, what's left on the right side? Just dt, right? Because there's just a 1. Now what? That seemed like it worked. Integrate. I like that. Ooh, I like that idea, Sean. We'll probably get there because we don't have the constants in terms of each other right now, but I like that idea. Can we integrate this? And it seems so ugly, but I can't stress this enough. What are G and K? So it's ugly. We should probably pick something to make this look a little nicer. What was that? So we don't need the constant on each side until we integrate. You're talking about the plus C part? So once we do the integral for sure. But how do we do the integral here? It's not nice. It's not just like x to the n right off the bat. I think you should do something. Cool. What do you want you to be? Louder. I heard a whisper. Was it you, Angel? Did you whisper G minus KV? Okay. That's what I would pick. Let's try it. What's du then? So even, what's the derivative of a constant G? Is it? It's just 0, right? So what's the derivative of 5x, for example? That's x, not v. 5. What's the derivative of kv then? It's just k. Negative k, thank you. dv, which means dv is just du over, or negative du over k. And it's weird because we have the different variable, but as long as you just relate it back to, oh, I know what derivative of 4 is in 4x, it's the same idea, just different letters. Is this going to work nicely? Question, Riley. Or am I just writing too small? Or both? Are you sure? Okay. What's the constant multiple that comes out of this? Negative 1 over k. Now, when I actually write this, and whether you actually write it or not is up to you, but I would actually write this like this, G minus KV, especially if you're struggling. And then dV I would normally write here. That way it makes it a little bit easier to see, oh, it's negative du over k. And now that constant's a little bit more obvious. But Fern, nice job. If you do not have to write this to make sure you can get the right constant, I'm okay with it. And that equals, I suppose I can help with this one, T plus C. Now, I made a silly, I wouldn't call it a mistake, but a miswriting. What should I have written right here? That's U. So I'm not gonna erase stuff. I'm just gonna try to salvage it with where I'm at. I now have the integral of 1 over u du. And what was my constant multiple again? Negative 1/k. And then, do you want me to write the integral symbol again with the u in it, or can we just do the integral? Okay, what's the integral of 1 over u? And u this whole time was G minus KV? Equals T plus C. Now, we have done, I would say, we've done the calculus part of this. But now, what are we actually trying to find? An equation for what? Somebody whispered it. I guess it was Angel because she's the person I can't see, but I can hear. V. We're looking for an equation for velocity, right? Well, let's solve this for velocity. And now we get to play the log game. So if you're rusty with logs, this is a good time to practice. What would you like to do first? We're trying to solve for V is the task at hand. Do we want to now separate and go up to the board so we can be making algebra mistakes like freely instead of just awkwardly waiting for me to tell you the answer? I like that choice. I'm going to pause right here. Your guys' job is to solve for V, not capital V. Cool. Board work, get up, go solve it. Make mistakes with the algebra, be wrong, embrace it. Cool, cool. I can move, Miss Sweet, if you'd. I'm going to make them tell me. Okay, I'm moving anyway, just so you know. So just to make sure before we move on too far past it, does it matter how fast you jump out of the helicopter? No, eventually who goes faster? Neither. They're going to meet at terminal velocity. Awesome. It's kind of neat, right? I think it's neat. If we got to this point, the algebra, I totally understand. You may want to just keep this, and I see a lot of people did it. If you stop here, you're not going to get the wrong answer, but your work is going to be very different. I'm just trying to see what was written on the other part of it. Minus G. This answer was the same answer that I got, just the ugly form of it. Like, I just want to stress that. This is the nice form of the same answer. Sorry, this. Now, when we plug in 0 for velocity and for time, this is what we get for C. Now, you guys naturally, because we just did the problem with 1.6 for that constant and whatever the initial velocity was, I don't remember the numbers off the top of my head, but that's what you guys did. If all that I needed was a way to write C, we just got it, right? This is our particular, or general solution, I'm sorry. And this is our particular solution that every object, K will be different because it all depends on how much of their area is hitting the air and stuff like that because it's a force that's being applied. So when we write our typical formula, we now have velocity equals G over K minus, or plus rather, I'm going to call it minus. What was C? So plus a negative, I'm going to say minus G over K to the power of what? Or sorry, there's C times what? E to the negative KT, right? Now, as we look at this, could we factor out a K from both of them? Or G over K. And then if we did that, I just want to look at something. So this is velocity. We have a G over K. What's it leave inside? And I lied. We're cool with that. 1 minus E to the negative KT. And if we took this derivative, could we take the derivative? What do you think we're going to get? I bet it winds up as this once we take the derivative. And now they loop back together. We just went through the whole process. If you could find the K value for any object, we just showed that this formula is true. Is what we did, whether you were aware of it or not. Okay, you guys had homework last night or no? Okay. I want you to do AP problems in 5.6 or 7. It's 5.7. 5.7 AP problems. Good news. We just finished what? That's right. Chapter 5 was just finished. End of 5.7. I don't know the page off the top of my head. I can't do it without moving my head back and forth at the same time. Yeesh, if you want to swing by at lunch, we should start looking at chess tournament stuff. Okay. Or fifth hour, free hour? We can talk 5th hour. Peace be with you.